Good morning, good afternoon, good evening, wherever you are in the world. This is the ECOMFIN webinar series at the ESSEC Business School, and I am Andrea Roncoroni, director of the center. Today, we have the pleasure to have Stephen Coe. Stephen is a professor, or Allen and Kelly Questrom Professor in Finance at the Boston University Questrom School of Business in the US. His research interests encompass fintech, quantitative finance, applied probability, and statistics, among others. And his work has been published in leading journals, including Management Science, Operations Research, Mathematical Finance, and Journal of Econometrics. Notably, his research on jump diffusion models has been integrated into commercial platforms, including Bloomberg terminals. In editorial capacities, Steve currently serves as co-editor for Digital Finance and associate editor for both Mathematical Finance and Operations Research. He has previously held editorial roles with journals including Management Science, Mathematics of Operations Research, and Journal of Business and Economic Statistics. He has also been department editor in the financial engineering area for the Operations Research. His contribution to the field have been recognized with honors, including the Erlen Prize from Informed Supply Probability Society and a fellowship in the Institute of Mathematical Statistics. Today, Steve is presenting a paper on Bitcoin mining and climate damage. Thanks for joining us, Stephen. It's a pleasure to have you here, and the stage is yours.
Thank you very much for inviting me to this wonderful platform. The paper I'm going to present is Bitcoin mining and climate damage. You can find the paper online, so SSRN, for example. The paper is joint work with several other people, Min Dai, Shuai Qian, and Lin Qing, all from Hong Kong. So let me go down a little bit. Okay, so now let me see okay. So now a little bit background about Bitcoin mining. So Bitcoin is first decentralized payment system on blockchain, and it requires mining in order to do this proof of work, which is used to prevent double spending. So when you do the Bitcoin mining, there are several things worth mentioning. First of all, you need to buy a special machine to do the mining, because now mining is very specialized. Then most likely you also join a pool to do the mining. So when you do the mining, you're going to have a cost. You have a one-time entry cost, which means you need to purchase a machine. Also, you have electricity consumption cost. That's your operating cost, right? Now the picture below shows two things. One is Bitcoin price, which is the blue line. That's the Bitcoin price up to the end of 2022. Then you have the Bitcoin mining revenue. Mining revenue means amount of money the Bitcoin miner might get. So they get mining in two resources. One is a block reward. So every 10 minutes or so, they get this award, which is quite large in magnitude of $10,000 in that magnitude right now. But this block reward will be halved every 3 or 4 years. So eventually the block reward will disappear. But on the other hand, they also collect the transaction fees. In other words, when you submit your transactions to do the blockchain, you have to do to be approved by the mining, and in doing so, you attach a tip to your transactions. The more tip you attach to your transactions, the more likely your transaction will be performed by miners faster. So the transaction fee is a big part of it, and it will become the only source for the mining revenue after 2150. So in about 100 years or so. So then that's the only revenue the Bitcoin mining might have, assume they still exist after 100 years. Okay. So that's the two types of revenues. One thing you notice that the mining revenue can go up and go down quite dramatically. For example, you have the first up and down around the end of 2017, then you have another one and around 2021. So it's not going to go up continuously. You just have this up and down movement. That's very important for our model purpose, as you'll see in a few minutes. So now, because you need to have this very special machines to do the mining, so now it's interesting to look at the computation power needed, how powerful the computer might need to do this. Again, the red line is the revenue you get from the Bitcoin mining. The blue line is computational power. Of course, as more and more people participate in mining, the computation power is getting bigger. It takes more power to do the mining. Therefore, you see the blue line is basically moving up, but you see it's not moving up monotonically. For example, here you have the blue line have a dip, and you have here too it have a dip from the peak. So the hash rate. So we measure the computation power by hash rate. Hash rate is not monotone. Okay, this one of the most important features in our model. So hash rate can be decreasing endogenously. So people might choose to reduce the computation power if you see the price is dropping and the revenue is not cover the cost. All right. So the key thing is why you have this dips in the hash rate. That because miner has option. Miner can exit mining. Right. If they exit, then there's less computer to do the mining. Therefore, the hash power gets reduced. Right. So this is an endogenous decision, which we'll be doing our model. So there's a control problem the miner need to solve. Now, the paper is about Bitcoin mining and climate damage. So let's see how much environmental cost this might do. So one way you look at this is you look at the electricity cost, right? So Bitcoin mining is consuming about 0.4% of global electricity. 0.4% global electricity means that, for example, a medium-sized country like Norway, okay, is about 0.4%. So you consume that much of electricity, 0.4%, about same size the electricity consumption from Norway. Now, the other thing you notice is, okay, the red line is this one is the electricity consumption. This one is hash power. So you see that hash power increased much faster than the electricity consumption. In other words, for same amount of electricity, the computation power is much more increased, right? So the reason is because you have technology innovation, right? So machines are getting better. For same amount of electricity, the machine is much more efficient now, right? So the second feature we have to notice is there's a technology innovation. The new machines are faster and consume less electricity per hash power, per computational power, right? So now there's some empirical studies related to the climate damage. For example, this paper published in Nature Climate Change journal. They have this claim, empirical claim that because the Bitcoin mining that might leave the global temperature about 2 degrees centigrade within a few decades, within the next 50 years or so. That will increase the temperature about 2%. But that's a bold claim, right? 2% increase in the global temperature, that's a lot, right? So that was a paper published about 7 years ago. Then there's a paper, 2022. So the first paper is not done by econometrician, is by scientists. This paper is done by econometrician. So this has time series model, etc., more closer to our field. So they did this empirical study, and the main claim there is the Bitcoin mining is not sustainable. Okay, so they have three criteria about current sustainability, which we'll mention later. For example, uh, what is the price you get from Bitcoin mining versus the damage it causes, right? If the ratio is bigger than one, then that means it's not the ratio is less than one is not sustainable, because the things you collect from Bitcoin mining is less than the damage it costs. So therefore, it might not be sustainable. So they have this three criteria about current environmental damage, which we'll review. Of course, is because it's a purely empirical study, no model. Therefore, they focus on current environment damage. They're not making predictions about what happens 50 years or 100 years from now, because to make predictions, you need to have a solid model, right? Empirical, you can look at what happened in the past. So there, they mainly look at what happened in the past, and in terms of current damage, it's already been done, right? Our paper will, in this regard, will focus on not only the current damage, but also focus on the future potential damage using model, right? By using model, you can make predictions, projections about what happened in the future. So their paper is about current environment damage. Okay. So now, what are the key questions we try to answer? We need to have a model talk about, okay, what's the connection about the Bitcoin mining and climate damage, right? We need to have a model to link the two. Now, once we have the model, we can let T become larger and larger, so we can study long-term climate damage, which was not possible if you just had an empirical model. Then we also going to incorporate two features we mentioned. One is miner has exit option, right, endogenously, and we also have technology innovation. Machine get better and better, right? So the damage will get less and less for the same amount of machine, right? Now, once we have this equilibrium model, so we're going to build a dynamic model, so we can come back to this question, says that, okay, so what is the long-term damage using model to answer this? In other words, we have a model that we will calibrate the parameters to the current data, to the past data. Then we use these calibrated parameters to make predictions about long-term climate damage. Right. Of course, when we calibrate data, we have to see how good the model fit the data, etc. But nevertheless, at least this is the first paper that have a dynamic equilibrium model first. Then from this model, we calibrate data and make prediction, right? Right. So that's the roadmap. In terms of the related literature, there's some theoretical literature in the industrial organization. They talk about, okay, firm, you have market, firm have the optimal entry, you have optimal exit. So firm can enter, can exit. This is like Bitcoin mining, right? So you have machine there. You can buy the machine to enter into this market of mining. Then you can also endogenously leave the market, exit, right? So that's exactly related to this Bitcoin mining, except in this IO literature, in the industrial organization literature, they don't discuss technology innovation, right? So all this famous paper, QJE, International Economic Review paper, they don't discuss technology innovation. Not because technology innovation is not important, it's because technology innovation make it very hard to study the problem. Because once you have technology innovation, that means every machine is different, right? The newer machine is better than old ones. Now, when you combine this with exit option, then you're going to have a strong path dependence. Because, for example, I have 10 machines here, right? I bought the 10 machine at different time point. The new machine are much more efficient, right? Now, if I decide to exit the market, then obviously I'm going to access I'm going to get rid of machines which are older, right? You're going to get rid of the old machine first before you get rid of new machine. That means I have to keep track every machine I purchase and put them a time tag, right? I have to know what time I purchase a machine, right? and that will be useful in making the exit decision. Therefore, it become a path-dependent control problem, right? That make it much harder to study. That's why this paper, they did not discuss the exit option. Fortunately, in mathematical finance, there is a related literature, totally different. So this is about the capital gain tax literature. So when you buy and sell stock, you pay the capital gain tax in some countries, right? Now in US, the capital tax is very complicated because you have the long-term capital gain versus short-term capital gain, right? So the asset you hold more than 1 year going to have a different tax rate than the asset you hold less than 1 year. Therefore, when you try to sell the asset, assume you buy this asset at different time point, you're going to have you're going to keep track of when you purchase assets. It's created time dependence as well, right? So so there's lots literature in the tax literature try to track the past dependency, right? Now we try to handle the same thing. Now in the tax literature, they cannot do this exactly. Complicated. Nobody can do that. Instead, they use approximations. So what would do is they use this average tax base uh, uh, approximation. So that's the tax system used in Canada, right? Instead of doing this long-term, short-term, etc., you just look at your average tax base, right? Then you pay tax according to that. So that's approximation. How good is that approximation? So all these papers published RFS and also Touzi and his PhD students, former PhD students, etc. They do this. So this first paper is in discrete time, then the other two papers are in continuous time. Then you have papers in management science or to study how good this approximation is. So in the general speaking, they found that although this is an approximation, but the bias seems to be small based on this approximation. Okay, so in other words, even if this is a hard problem, but at least in the tax literature, they have an approximation to study this. So if you talk about one sentence about our economic model, it's essentially we borrow this to here. In other words, we add this technology innovation to the existing industrial organization model. Then, of course, we cannot solve the problem. Then we use approximations, this average tax cost approximation to solve the problem. Then we put this in the setting of the Bitcoin mining, then try to do the model building and also calibration, etc. So that's the roadmap. We borrow the tax literature, borrow from tax literature to study the industrial organization model so that it can be used in the Bitcoin mining. Okay, so that's the roadmap. So now a brief review. So I already mentioned this empirical paper, right? So these are all empirical. They studied of current climate damage, not about long-term sustainability, right? There's this paper in the JP, Journal of Political Economy, by Pratt from Ecole Polytechnique. So there, they have technology innovation, but they don't have exit option. Because they don't have exit option, they don't have this time path dependent issue. They only have entry. But this one is different from what we observe empirically, because as I showed you before, the hash rate can go down. That means the miner indeed has the miners indeed have exit option, right? So the JP paper simply ignore this option because otherwise they cannot solve this. So so that's the key difference between our paper and the JP paper. Of course, there are also other studies about empirical studies, not theoretical, about electricity consumption related to Bitcoin. For example, in particular, Cambridge University in UK had this Bitcoin electricity consumption index, which is used in our empirical study. Okay, so that's related literature. In short, this is the first dynamic equilibrium paper on climate damage of Bitcoin mining. We can make predictions about long-term damage, and our according model, Bitcoin mining is not long-term sustainable in terms of the climate damage. So something has to be done, not at current rate. And in terms of current climate damage, by and large, we confirm the empirical study done before regarding the current climate damage, although their paper they discuss long-term climate damage. Now, in terms of mathematics, we borrow the singular control literature from the mathematical finance related to tax, capital gain tax, so that's our contribution. And our paper is the first paper on the industrial organization, has entry, exit, and technology innovation in one framework. So that's this. In terms of the difficulty in mathematics, well, although we borrow a lot from the singular control from the text literature, but there's one technical issue is in that literature, they don't have the issue about unboundedness in terms of particular utility functions. We have to address that. Okay, so we have to extend their result a little bit in terms of viscosity solution, etc. That's in the online supplement. Okay, so there's some small technical issues we have to solve when we try to solve this singular control problem. It's singular control because there's a region you don't do anything, then once you exit the region, you're going to do something. Actually, there's several regions like that. Okay, so if you any questions before I move on to mathematics?
No, it's clear. To me, it's clear.
Okay, clear. Okay, good. So now let's try to do some mathematics. So this slide is essentially the same thing as the Pratt's water JP paper. So you have miner, have revenue. Revenue from this is exogenous specified. So in other words, we do not model the Bitcoin price. That's too complicated for this model, for this paper. So we'll take it as a JP paper. So revenue is a geometric bound motion. We're going to estimate alpha, sigma, but that's it. Now, of course, if you look at real Bitcoins, you have lots of geometry diffusion, etc. Right? So we discuss some of them in online supplement, but for simplicity, let's start with geometric bound motion to begin with. And the reason is because we're going to study the long-term damage, right? So we focus on diffusion part probably enough. Now you have the revenue exogenous given. Then when you have a miner enter this, you have two type of costs: one term entry cost and the operating cost. That means you have electricity. Okay, so the one-time entry cost is given by exponential function. Why you have the A here? Well, A indicates the machine getting better and better, right? So the cost of same hash power will be getting better, right? Decay exponentially. So that's this. And you also have the operating cost. The electricity cost also given by this. Okay, the operating cost per hash. This called per hash. Now later we're going to link this more closely to the empirical observed electricity price, but that's in the extension of the model later. Okay, but for the very basic ones, you have this, and also for the very basic one, we're going to take the exact assumption as the Pratt have this A here and the A here are the same. Although when we do the empirical things, we're going to relax this a little bit. So this same parameter A control both as in the JP paper. Okay. Now we're going to talk about how the exit happens. Now assume that when you sell the machine is going to be zero. So there's no resale value of machine when you try to get rid of machine. And of course, we're going to use the average base as approximation. So the average base in the text means that you can compute the average cost when you try to report the capital gain tax. Here's the same thing. We're going to assume that when you try to get rid of machines, you're going to get rid of the same fraction amount of different machines. So in other words, suppose say I'm going to reduce my cost by 10%. I'm going to get rid of 10% machines I bought last year, 10% machine I bought this year. Okay, of course, immediately this will create bias because when you try to get rid of machines, you obviously it makes sense to get rid of the old machine first before you get rid of the new machine, right? But that's exactly as a tax literature. Then you have to keep track of all this long-term capital gain, short-term capital. You have to keep track of this. Now you're going to have insolvable mathematical problem, but by using the average one, at least it only increase the dimension of one, so you still can solve it. Of course, led to bias. Okay, now the bias obvious you're going to have you should get rid of fewer new machines than should have been, right? So now we're going to have a correctional bias. So in order you do this, you're going to have two fewer new machines. Right? So now what we do is we're going to have this parameter rho here that denote the entries, exogenous entries. So this exogenous entries serve two roles. First is going to correct our bias due to this approximation. Secondly, it also capture a interesting phenomena about exogenous entry. So part of the entry is endogenous, part of the entry is exogenous. Why you have this exogenous? That's because in practice, there some miners they keep on buying the machines irrespective of the Bitcoin price. The reason is because of renewable energies. There, for example, there people doing minings using the solar powers, right? So use the solar powers, and there actually people become rich just because do this convert solar power to Bitcoin price. In some sense, the Bitcoin mining is an economic battery people use to store the electricity they generate from the solar powers in some sense. But the solar power is widely known is very volatile, right? Very volatile because depending on the weather conditions, you might have you have a large output of solar power, a small output. So this create a significant challenge for the national grids. So many countries has regulations that all this solar power cannot go to the national grids directly because that creates so much volatility in the voltage, right? So it's difficult for this company to get solar power to get in the grid directly. Then some of the companies just said, okay, forget about that. When I generate electricity by using solar power, I just use that to do Bitcoin mining to store that economically. So that's created a demand for all this entry, irrespective to the Bitcoin price. So this role here is also try to capture that phenomenon. So role has two purposes. One is to make a correction. One is to capture this exogenous entry because of renewable resources. Okay, so now what is hash rate? Well, the computational power. The hash rate will have these two controls because you decide entry, you decide exit. So now L, so similar to the temperature, we're going to have two right continuous left limit exists, non-decreasing adapted process. L is entry. So L, you have two control process, L and M. These are singular control, so you have two. L is entry. You decide how you're going to enter this, right? L is cumulative entry. And M is decrease in terms of the hash rate. How many the proportion things you're going to get rid of, right? So that's this. So the M is proportional, L is absolute, right? So this so you have L M, and for every L you get into that Q increase, and for every M you get rid of, right? So Q decrease. Okay, then you have this exogenous entry, as I said, right? Row here, there try to capture the exogenous entry and also this correction for bias. So that's the hash rate. Then you have the cost. Okay, the operating cost. This mainly electricity cost. So cost, you're going to have the electricity cost here and the purchase cost, right? So you're going to purchase a machine, okay? If you purchase the machine at time t, this is the cost for buying the machine. Now, if you get rid of the machine, you're going to save some money, right? So that's why you get minus KT here. That's because for every machine you get rid of, you're not going to incur the operating cost anymore. So that's this. And for every machine, so for every entrance there, then you're going to for every entrance here, every row here, you're going to buy this machine, so you're going to have the CT cost there. So that's this. Now, so so this is the cost we borrow from the average cost, and as I said, borrow from the tax literature. Okay, continuous time tax literature. So now, how do we define equilibrium? Okay, so how do we define equilibrium? We take the definition in the existing literature. Dynamic equilibrium means that the new miner will enter the market if or only if the new miner will compute the discounted future revenue, and if discounted future revenue is bigger or equal than the future operating cost plus the machine purchase fixed cost, then the miner will be enter the market because it's more profitable to do mining. In equilibrium, no new miner come to market. So in equilibrium, the exactly the opposite inequality must happen, right? And similarly, a miner will exit the market if the future revenue is less than the operating cost. So in other words, it does not make sense to sustain this to do the business anymore. The miner will exit this. So to reach equilibrium, no miner will exit anymore. So the reverse sign must happen. So the equilibrium will consist of these two conditions, right? Now you can convert these two conditions by using the notation we just showed in the previous slides. So you're going to have this. That's the first inequality. That's the second inequality, right? So that's this, right? So that's your you have this dynamic equilibrium, right? So you have this, and so this is the case rho equals 0, and if you rho positive, similar definition can be written in the online appendix. So now what's your objective? So similar to the Lucas principle econometric paper, we define you have one social planner, try to maximize discount expectation of the societal surplus, right? So now this is your discount, and you have some surplus. So when all these things here are standard, except this term here. So this sounds weird. We never mention anything about log utility. Where did this come from? Okay, this is because if you look at the consumer surplus, so starting from any delta to QT, then you have this RT, revenue divided by QDQ. This integral is equal to this. And the second term here can be dropped because the second term does not depend on the control. You have control LT and MT. The second term does not depend on that. So the only thing left is this term here for every delta. Therefore, Lucas and Prescott, they just say, okay, instead of this term, you simply maximize with respect to that, okay? So that's this. And this, so that's the consumer surplus. Okay, the other two things is about, okay, the operating cost and entry thing. Okay, so that's this. And for this to be have final value, you have to have some conditions. The discount rate must be large enough for this integral to exist. So this is nothing new here. This is taken from 71 econometric paper. So the first theorem is you can prove that if a social planner doing this social planner optimization problem will give you industrial equilibrium, and industrial equilibrium is defined to be this, right? So in other words, if somebody try to maximize this utility function, that solution is the equilibrium solution. Okay, of course, there's a limitation to this theorem. This theorem does not tell you there is a unique equilibrium. No. It just said that the social planar solution is one of this equilibrium. Therefore, for our purpose, we can focus on this social planar problem. Okay, because whatever solution you get, this one person stochastic control problem will at least be an equilibrium solution. Okay, so for the rest of the paper, we just focus on the social planarness stochastic control problem, singular stochastic control problem. So that's, you write down the HAB equation, Hamilton-Jacobi-Bellman equation, though that's your original problem, the social planar problem, right? Then the HAB equation is this, okay? Now, you have few terms, just like single control, right? You have few terms, 1, 2, 3. You have 3 terms. The minimum of these 3 terms equal to 0, right? And this is your generator, right? So this is your diffusion term, this is your drift term, and this term come here from your dynamics, okay? So that's your HAB equation singular. Now, because this HAB equation has 3 terms inside, therefore you're going to have regions, 3 regions, right? So, oh, by the way, before I discuss region, so this HAB equation does not admit closed form solution unless you have special conditions. For example, suppose there's no fixed cost, then the HAB equation has a very simple closed form solution. Okay, and here's a simple control strategy, but this is not realistic because you have fixed costs. The other case is you don't have technology innovation. If A equals 0, here you have closed form solution. So this is not very useful, but this special cases can be used as a benchmark to see whether our numerical solutions give you the right answer or not. Okay, so these are 2 special cases you have a new solution, but otherwise you're not going to do this. One particular challenge that's, as I said at the beginning, we make a little bit contribution into the methodology contribution. So this HAB equation has infinite number of solutions. So for example, any of this form will be a solution of HAB equation. So the question is, which solution you're going to choose for that optimal stochastic control problem, right? So here's the second solution. So among the solutions, you're going to choose a minimal solution. So you have infinite number of solutions to the SAB equation in terms of viscosity solution. You're going to choose the minimum one, the smallest one. So that's in terms of series. So in other words, the smallest solution in terms of the viscosity solution indeed is your solution for the original stochastic control problem. So that's first part of the theorem. The second thing is, how do you get this solution numerically? How do you get this solution numerically? How do you get this minimal solution numerically? The thing is, if you do the penalty method, simple penalty method, finite difference penalty method, that finite method, as mesh goes to 0, will exactly convert to this minimal solution. So that's nice, right? In other words, you do this penalty method from the finite difference, then that method numerically will convert to this minimal solution, and the minimal solution is exactly the solution you want for the stochastic control problem. So that's give a theoretical foundation for the method we're going to do for this stochastic control problem. So of course, to prove this, there's some technical difficulties, such as unboundedness, etc. So this is different from the existing one, because the existing one requires bounded of utility functions, etc. But our solution not. Okay. So now this next 2 slides, just small technical details. You can originally you have control. You can do a change of variable. you divide everything by Q, you can reduce dimension by 1, you get 2-dimensional problems. Okay, so that's become your 2-dimensional problem. So now from this, you have 3 regions: no action region, entry region, exit region, and there's a special region called upgrade region, which means you're going to sell everything. So let me show the picture here. That's your control policy here. So if you here in the no action region, you don't do anything. You don't do anything, okay? You don't do anything, you stay there. Then here, if you in this entry region, for example here, you immediately buy the machine to get in the boundary. You immediately going from A to B. Now, if you in this X region here, like C here, you immediately sell the machine. You immediately sell the machine, then you're going to go to boundary. Now there's this region here. You see this region has this feature. So it's part of this exit region, but it's so special that in this region means that you sell 100% of the machine. You totally get rid of all the machines. Okay, in this, so here you get rid of some machines. Here you get rid of all the machines. But this, I mean, from the HGB equation, it's still in the exit region, but the exit region is so large. Okay, so get rid of this. So you have entry, exit, and no action region. Essentially, that's your control policy, right? So that's this. Now go to once you have a solution, you can discuss some interesting properties. For example, in your optimal solution, the total operating cost, the ratio of total operating cost and the revenue rate is bounded above and bounded below by some constant dependent parameter. So this means that the optimal rate of the total operating cost and minus revenue, they are on the same order. Right? The minus revenue is same order. Okay, so that's it. And notice that revenue is exogenous thing, is driven by this geometric bound motion, right? So in other words, the total operating cost that's endogenously chosen one is about same magnitude of the geometric bound motion, the revenue to get, right? Right. So for this, you can discuss. So here you already have this properties. So this in our model, but in the entry-only model, this is not true. In the entry-only model, in other words, if you don't have exit options, the ratio of the two will be unbounded. Okay, the cost might be because what happens if you buy all these machines, you cannot get rid of machines. All these old machines become so efficient, and you cannot get rid of that. Then the cost just blow up to infinity. Okay, so that's this. So here, I still have about 10 minutes or so. So let's look at empirical result. So we get data. Okay, we get about data here, 4-year data here about Bitcoin price hash function, etc. The blue line is hash function, the red one is revenue. Okay. Then we calibrate this to figure out what's the parameter for geometric bound motion for the revenue. Then we do the calibration, we solve the stochastic control problem, then we try to calibrate to this, the observed hash function. So this observed, we try to do the endogenous control problem and try to this, but you minimize the least square, right? So we do this, we try to minimize this. So here is our calibration result. Okay. The black line here, is the observed historical data. The blue line is our recalibration based on the JP paper. You remember JP paper has no exit option, so the blue line can only increase. No exit. The hash function can only increase. So that's this blue line here, only increase. The red one is our model. Our model can have both entry and exit. So our model can go up and going down. Okay, you especially look at here, it can go down. Okay, so that's make it better fit to the data. In fact, if you look at some summary statistics, the the mean square error, L2 distance, for our model is about 7% in sample, A sample, out sample. Out sample means here. So we use about 9 months data as out sample. So here is out sample, right? So this is about 40% of the error you get from entry-only model. Okay, and here's the standard deviation for this. We get standard deviation by using bootstrap method resampling. Okay, so that's this in terms of fitting to this. Now, secondly, we look at parameters. So compared to entry-only one, we get different set of parameters. For example, our parameter A is about 0.5, and their parameter is about 0.9. Now, A has a meaning, that's a decay of the machine price. So if you look at average technology innovation, you can look at machine price. So machine price decreased about 37% per year, with 95% common interval to be this. So our 0.52 is within this 95% common interval, but theirs is not. So that also means that not only we calibrate the model better, but our parameter make more sense compared to theirs. Okay. So now we link to the climate damage. So we said that climate damage is equal to the electricity cost plus the carbon price, which the standard thing in literature they use is $100, okay, times the emission intensity, okay. So in order to generate electricity, how much the carbon is going to produce. So there's a data, right? So they have monster data given by this. You can get from the Cambridge Bitcoin this. So we're going to have two approaches, okay. The direct approach means that, okay, we have the model implied total operating cost. So the model will give you K, okay. Then you also have the observed daily electricity price, okay. Then you can immediately compute the electricity cost here. So that's direct one. So you plug in this here. So that's direct one. So you have KT, you observe empirical electricity price average, then you take the ratio of 2, you get this. So that's the direct approach. The indirect approach is you simply look at the hash rate. So you don't look at KT, but you look at the hash rate QT. Then you assume that, so these people, they make a big assumption. So suppose efficiency decays exponentially with this parameter AE, then you can estimate the electricity price by using the QT. So because QT can also observe, okay. So that's this. So we try both direct approach and indirect approach. So now here you look at the direct approach and indirect approach by using different models. So for example, you can use the Cambridge empirical study there. So that's black one. And you look at entry model, the blue line, and our model, red one. So what happens, you see, our model will, in general, will give you less environmental damage, climate damage. That's simply because our model has exit option. With exit options, you're going to cause less damage, right? Because you get rid of machines, right? So that's this. So that's, you have direct approach and indirect approach. The shape of this looks similar. The number might be slightly off, but the shape looks similar, whether you use the direct approach or indirect approach, okay? Now, we try to see two things, the current climate damage and the long-term climate damage. So this current climate damage, they propose 3 criteria. We're going to use this 3, and let's look at a table here, so that's easy, okay? So in their paper, they propose 3 criteria. What's the growth rate for the damage? You look at the probability, whether the damage divided by ratio bigger than 100 or not. What's the probability of this? And you look at the expectation of damage price ratio. So that's their three criteria. Okay, so now you have things there. So you have the direct approach, indirect approach, that's two things. And that you have their paper, CGB paper, they compute all these numbers here. And now we have four things. Our model, entry-only model, the Cambridge one, the Cambridge data, because you can use the Cambridge data to you can use Cambridge data to just do empirically. You have this, okay. So these are different numbers you get for the per coin mined and also for the per coin revenue. So there's slightly different ways you can compute that, right? One when one just look at the block reward, the other one also look at transaction fees. Okay, so numbers are different, but they all give you the same conclusions. In other words, they all said that okay, look at this, the expected damage price ratio is all above 50% to large extent, and this worse than natural gas. Natural gas is about 46%. All these things say that this will worsen the natural gas, and all the thing here also says worsen the natural gas. So in other words, we confirm their message that the current climate damage is worse than the natural gas damage is. Okay, so that's confirmed there. And now you can look at long-term climate damage. This you need a model, right? So now for long-term, you also need to have the model for electricity. So we use, for example, electricity model in the standard papers. Okay, so you have the deterministic function account for seasonality. Then you have the growth rate. Then you have some geometry diffusion, mean reverting geometry diffusion. You have spike, then come back down. So the picture like this, right? So that's this mean reverting jump diffusion, right? So that's this, right? So that's because you see every time you have a spike, then this will you have this mean reverting parameter will get you back down, right? So that's this. So you have spike, long-term growth rate, and determined function. So that's electricity. So then we cover this. We have serum here. So long term, you have direct approach, indirect approach. You get similar answers. They give you conditions. If this condition satisfied, the climate damage will blow up. Okay. In the indirect approach, if this condition satisfied, the climate damage will blow up. So the all amount to whether the parameter check satisfy this condition or not. Now, for our caliper parameter, the left-hand side is 17%. Right-hand side is the inflation. Now, inflation not going to be 17%, so this condition satisfied. So the long-term damage will blow up, goes to infinity. So long-term damage divided by the inflation rate will go to infinity, depending on direct approach. For indirect approach, similar thing. In our calibration, the minimum of this parameter is 53%, much higher than the inflation rate. So again, long-term damage will blow up from Bitcoin mining. Okay, doesn't matter we look at direct approach or indirect approach based on our calibration of parameters. Okay, so this also says that okay, the difference between our model and entry-only model. Roughly speaking, our model is only the environment damage from our model is only about half of the entry-only model. So the changes over the times in our prediction because the electricity price will fluctuate, etc. in our simulation. So this gives you simple illustration. Okay, so the mean is about here. So this tells the difference between the two models. Okay. Although look at fluctuate a little bit, but it just said because the exit decision also fluctuate, right? So that's this. So now good. I have 1 minute left. I just do the conclusion. So we have a dynamic model, equilibrium model for Bitcoin mining with entry, exit, and technology innovation, right? Exogenous entries. The model can explain the co-movements of Bitcoin hash rate and mining. Now, into mathematics, we overcome some difficulties related to viscous solutions because you have infinite number of solutions, the minimal solution, etc. Right? Now, the economic conclusion is based on our data. based on our model calibration, we say that Bitcoin mining is unsustainable in terms of climate damage, both short-term, confirm the existing result, and the new result, even in long run, is not going to be sustainable based on the current data. Okay, so I stop here. Any question, I'm happy to answer.
Thank you, Stephen. Is there any question in our audience? Faisal?
I have one question, Andrea.
Hi, Faisal.
Hi, can you hear me well?
Yes, perfectly.
Yeah.
Nice. Thanks, Stephen, for the great talk. I just had one question, which is to what extent is the model applicable to proof of stake blockchains? Or are you thinking of maybe writing either a new paper or an extension of the model to take into account this? And also, would you expect the results to differ especially for the long run under a proof of stake kind of protocol? Thank you.
Yeah, this is a very, very interesting question because here we focus on mining, right? So there, as you mentioned, there are two types of things, right? Proof of work and proof of stake, right? So this is only proof of work,
Yes.
right?
Yeah.
You do the mining, you do this. Proof of stake, different thing, right? Because for proof of stake, you're not going to do the mining, right? Right?
Yes.
You're not going. So the damage to the environment is a totally different thing, right? So this one you need to do all this useless puzzle solving related to mining, right? So you waste your
True.
computation power just to do this proof of work, right? So they just said, what you say, how much damage is this useless work compared to revenue generated? That's the thing we discuss here, right? So the
Yeah.
paper is not relevant
Yeah.
to the proof of work, essentially. Yeah.
Okay. There is a little bit of computational burden in proof of stake, but clearly there is it's less. But there is
Right.
maybe welfare loss in terms of money stuck in the blockchain. In proof of stake blockchains, you have billions of dollars stuck in what's called stake. So maybe that has some kind of a negative effect. But anyway,
Right.
thank you. Yeah,
Right.
you
So
are right.
that's different. Yeah. Thank you.
Thank you.
Yeah.
Stephen, I have a couple of questions. The first is, can you foresee in the model you presented some point which might be changed or maybe something that could be added, I don't know, that might undermine this catastrophic outcome? So something that gives a kind of hope in a sense. And the second question is, so maybe some limitation of the model that is determinant in this result about unsustainability in the short as well as in the long run. And the second point is, if this is unsustainable, can the model be modified, or I would say extended, to the general situation of excess of consumption of electricity by AI? And last, what if there is a technological step forward, like imagine the quantum computing becomes available to anyone and there is no problem of stability of the current machines, and then this dramatically drops the difficulty or the need of electricity required to make this computation. I mean, could this help in the short run? Or you say that then all problems will be scaled up and will be still very energy consuming, even for quantum computing? Maybe
Okay, very good question.
Too many questions.
I can answer. This all very nice question. So this whole question can be boiled down to one equation. I show you this, then we're on the same foot to try to answer the question. So the key result, the key insight. Let me show you. Okay, the key insight is actually this equation here. Yes, this equation here. So this is a key insight. The key insight is, okay, you have this endogenous control problem, right? whatever the control problem you solve, you find out that's my optimal cost. That's your KT here, right? That's my ideal cost. The ideal cost, ratio ideal cost, and the revenue I get from the Bitcoin mining is on the same magnitude, right? So that's etc. So now, why we have this result, Bitcoin mining, that's the symbol. Now you see, if you believe this result, then everything makes sense, because in our model, what is RT? RT is not modeled. RT is coming from this geometric boundary motion, right? Right?
Yeah.
So, and then what's the drift of this RT? Based on last 20 years data, the drift of RT is quite large, 40%, right? The Bitcoin price is starting from virtually zero to now about $80,000, right? So RT has about 48% annual growth rate per year, right? Right? So because the ratio of two is the same, I mean, same magnitude. So because RT has such large growth rate, so the cost, the operating costs, they also grow very large, right? Because they grow at the same rate. You have lower bound 80 here, right? 8 here, right? So that's cost is grows so much, right? Now, if you look at environmental damage, because cost grows so much, then of course environmental damage is going to be large too, right? Right? Now, the model could tell a totally different story. If, for example, 20 years down the road, the RT go down dramatically. For example, it may be 20 years from now, nobody going to do anything with Bitcoin, right? Suddenly, the Bitcoin, the exponential blow up of Bitcoin will disappear. Then, of course, I believe, of course, you need a different model, but this message generally probably true. The operating cost and the operating revenue should be on the same magnitude. Because nobody is stupid, right? So if I can only make $10, why should I spend $20 for a cost, right? Make no sense, right? So now, for more general models, this should also be true. KT, even if we do not do in this paper, but KT over RT should be on the same magnitude. So of course, if the Bitcoin revenue go down dramatically, the environment damage will also go down dramatically, right?
Sure.
So in other words, the long-term sustainability of this all depend on what's your prediction about the future of Bitcoin, right?
Exactly.
In Bitcoin, right? So that's I guess this will make sense, right? Right?
Yeah, yeah.
Right. And
So
this also answer at least several of your questions, right? So what happens if people more interested in Bitcoin, and of course environment damage will be even more, because right? If
yeah,
the less interest because quantum computing, etc., then the cost will go down dramatically, right?
dramatically. Yeah,
Yeah,
definitely. Clear.
yeah.
Okay. Well, it could go down and even to zero, because if KT
Yeah.
becomes zero, then
Right.
A would be zero, but A here is said to be positive. Yeah, so
Yeah, A is a constant. A is a constant dependent parameter. So A
yeah,
is
but can it be
positive, right?
zero? Can A be zero?
Unlikely, but so A in our paper we have a explicit formula for A, right? So you have A there. A depends on some parameters there. For example,
Okay.
the drift of Brown motion, etc. So you can plug in number to see whether. But A is a positive number. Of
Yeah.
course, we're not saying the limit of A maybe goes to zero or not, right? Right.
Sure.
A is yeah.
Okay. Thank you very much, Stephen. Very exciting,
Okay.
interesting, and on topic.
There's one chat. Oh, thank you. Okay, fine.
Yeah, no,
Good.
it was
Thank you.
Faisal that was telling us goodbye.
Okay.
Let
Okay.
me